Okay, so depending on if you're familiar with the unit or not, this we got a couple different visuals on the unit, but the big sweeping comments I actually want to point to over here is that this unit is on power production, electricity, magnetism, power production, and climate science. And so kind of the big overview highlight is having some fun with electricity and magnetism. We make electric motors, electric generators, electric guitars. And, this is a culminating unit. There is unit 7, which if you haven't done it, it's a great way to end the year, but we have already sprinkled it in. And so it's really 3 2-day lesson progressions. So you could do 1-2 days before the end of the semester if you don't have time to start up a new unit. But in any case, unit 6 really is the culminating one. Unit 7 is really great. It's totally revamped, have gotten such positive reviews. That's space in the universe. I should say that it's space in the universe. So it's super fun. Just kind of high engagement in a different way. It doesn't have the 5-paragraph essay that this one has, which you can decide if that's the right fit for your students. But in any case, this unit 6 really is the culminating sort of intellectual rigor unit for the course. So that, we have our final data informed design in the engineering section. There's some new patterns. We have used those 4 patterns, but what a great way, especially in chemistry and biology, they're going to see new patterns. And it is optional, but and we'll say it during the webinar, but just to put that out there, that here's a chance to say the world is big and amazing, and there's even more patterns than what we've talked about so far this year. And then, of course, climate change and climate science. So that's a big piece of the driver of this unit. Okay, so we got the feedback, years ago now to really sort of bullet in the agenda all the little highlights, because people just wanted to see it in writing because it happens fast. So here really is just about every bullet, and I don't think it makes sense to read those to you. So we are going to just dive in to the anchoring experience, and we probably won't come back to the agenda, but do encourage you to have the agenda open. But there's a couple times. So the first thing, though, to show before we dive in is the idea capture tool, which I did show, and just want to encourage, if you have resources to share or questions, please put them in. Today's slides are right there, and then the teacher calendar. So here it is on the website. There is another overview, full video, short video, a student calendar. Here is all of those performance expectations. This is the biggest unit by far. We've been building up to this, and we're ready to have students be successful with it. The other overview image that's really powerful that I'll take 60 seconds on is that, this all starts with, how do we make a 50-year energy plan for Oregon? So it does start with a Voices of the World that brings up different perspectives from people around the world, excerpts. And we're going to say that right after I finish this. So I'll just leave it at that. They look at different perspectives on climate change and power production and the effects of that. Then just coming off of Unit 5 with Sound and Waves, they build a speaker. And that's really important because that's where they learn about electricity and magnetism. So it's really nice. The speaker's really fun. The storyline, though, and then they flip that motor around and realize they built a generator as well. And that's important because we are talking about making a 50-year energy plan for Oregon. So we need to understand the physics of generators. And that's something we've seen in all of the engineering portfolios. There's a little bit of background information always. Then the storyline takes us that, as cool as it is, I mean, it would be amazing if we could power the world off of electric guitars, but we can't. So when you make generators, you really need to scale them up when we're talking about powering societies. And so that takes us and launches us into our engineering project around the wind turbine. Really neat student talk, engineering talk. Then also, because if you look closely at the performance expectations and you look at the 2 fastest growing power production means, that's wind and solar. So we wanted to have a small engineering project around solar, and we really call it an engineering slice. It really is a 2-day engineering slice. And we'll say more about that. Then, having gotten this far in the storyline, early on, they had already analyzed the economic impact, the sort of land use impact, but we haven't so far analyzed the climate impact. And of course, we have way more goals than just that with this climate science aspect. But again, it fits nicely into the storyline that, okay, we've looked at how generators work. We've talked some about scaling them up to this amount that we need to power the world. And then let's look at the climate impact. And there, of course, is a lot more earth science standards that we cover in that dive. And then it culminates with them doing a different type of computational thinking. They don't do any coding this time. So they're just using their brain and a computer very quickly, which, I know a lot of, we've talked, I'm sure everyone's talked a little bit about, chat, GDP and AI. Anyways, certainly everyone now thinks that the human brain and a computer working together can output something. So we do that with computational thinking in this 50-year energy plan. All right, with that, that's kind of the overview. So now we're going to, again, looking at the teacher calendar, we're going to now look at the more lesson level. And this first lesson is 2 periods. And I will turn it over to Matt to give an introduction there.
Yeah, thanks, Bradford. So in the first lesson, 2 days of class, we are trying to humanize this problem, and also recognizing that climate science, power production, and electricity, they affect people all around the world. And so we start this day, first day, looking at composite people who are real, and there's an excerpt from them from all around the world. And students take on, to varying degrees of success, take on the roles of these people. But this is a day when really in the spring of our, at the end of the year, students are really thrive with this. They take on a role and they need to find people from around the world who was like their character. So you can see on the screen that Bradford's showing there at the top, they take on one of the roles and they say where they're from, they read it, and they come up with like, what's the most important to them? What other important details? And then they get in groups, and lots of times we have groups of, 6 to 8, kind of a bigger circles, and have them get together and share out who their character is, and find out what's important to them from somewhere else. Then we'll shuffle those groups, kind of jigsaw, maybe get in another group of 6 to 8 and share again and see, who's somebody who's affected by climate change in the same way, who's somebody who has a solution to climate change. Lots of visionary people and people who are being affected around the world. And then that gives them a context that this is a real world problem, and it really is affecting people all around. So we start with that we want to build empathy with students, see the perspective of people from around the world. And then what we want to do is we want to launch into kind of harnessing the understanding of what's the problem that we are trying to face, what's the problem that we are solving here. And I'll let Bradford introduce that.
Great. So that is our 50-year energy plan portfolio. And it is the 2020 up. 2022 has been released. It always lags a little bit, but those will be updated. But that was just recently released. And so they read excerpts from the actual State of Oregon Energy Report. And the new report still does reference the older reports, but also has updated numbers. And like so often in our engineering projects, they get put in an energy plan commission. And so, there is some new laws, and that has actually already been updated. And we were able to talk with professors at Oregon State University and PGE about those, what they're going to do to meet those, getting off of coal or yeah,
Fossil fuels.
yeah, fossil fuels. Thank you. All right. So, and then this looks pretty familiar, right? So problem statement, constraints, criteria. If it is new to you, I'll just say that a lot of people felt like this was the moment where it really solidified for students about the constraints. You know, again, as we just said, the clean energy and coal transition plan, getting off fossil fuels by 2040. That's a clear constraint. And then criteria, you know, we want one that reduces the climate impact, and more the better. So in any case, those are ones. And like always, we want that initial plan, that 50-year energy plan. So, and this one is, I mean, sometimes they'll say like 100% solar next year, and that's good. And, you know, throughout the unit, they get to be more holistic in their analysis. Okay, so with that, we don't want to dive too deep on this, so I'm going to pull back there and say one last piece in this intro sort of couple days for the unit is they might not be that familiar with natural gas, biomass, geothermal. So there's an activity that has them explore, and there's a great website. It's linked. I'm in the packet right now, and it's linked here. And so they go and you jigsaw it. And so students will investigate hydro, coal, natural gas. These are actually in the order of the percentage that they currently are in the state of Oregon. So that's where that ordering is coming from. And then they go to that website, which has a lot of great stuff. But just to show geothermal, whoa, it's acting up a little bit for me. Click on that, and it gets customized. And the nice thing that I wanted to point out was just that for each source, it has a written description, a short video that's just like 2 to 3 minutes on each one. And there's this interactive map that since I've clicked on just that one, it's already kind of, I don't know what to call this style of map, but anyways, click on alternative energy and it brings up all of these other ones. All right, so that's another piece of the puzzle. So there's this broad, okay, we did Voices of the World and had that chance to talk about a more global perspective on this. And then they get introduced to the actual project. And then there's some background of the different power production means as they are. But we're about to take a deeper dive into the physics targets that we actually need, but in a very fun way. So I was going to take the speakers and I'll hand it off to oh yeah, go ahead. Actually, why don't you
just
jump
say something and I'll
yeah,
do this. Yeah, just to know, Bedford, can you go back 2 tabs? That these if you scroll up just a little bit, the criterion number 1, number 2, number 3, those were introduced in the problem statement, in the problem. And so they know what those criteria are, what their plan is going to be measured by: cost, land use, and climate impact. And they actually rank those within the first day. They're deciding, you know, what is most important to them. And of those 3, what's most important and what can be left behind. And then they are going into doing that research on, you know, coal, natural gas, biofuels, all of those things. They're going into that research with some context. Oh, I'm looking for how much it costs. I'm looking for how much land it's impacting, or the climate impact as well. So those 3 criterion are there intentionally to, you know, the description is the general idea, and then there's those 3 criterion. There are very targeted notes there. But as Bradford was saying, we have students coming in with some familiarity with some of these and some with not. But very few of our students have had a chance to learn in depth about electricity, what electricity is. And so we want to give them a little bit of background before we dive into more complicated energy generation and things like that. So we go into, Bradford, if you go over one more tab there to the Google Slides.
Okay.
Yeah, so we start electricity with an analogy, a water bucket analogy. This is an analogy that we use to kind of to demo and interact with and see, how does electricity work? And so how this works is we have a bucket at the front of the room and a bucket at the back of the room, and it's full of water. One trick that we use, just a drop of food coloring in each bucket, and sometimes in the empty bucket, we'll put in, like, let's say there's blue food coloring in the front, we may put in some green food coloring in the back, so that when the energy transforms, it changes color. And so you have this, the switch is turned on. All the students on the bottom side are high voltage. They have lots of energy. They are representing the electrons that are traveling. And the battery is on the right there, and the bucket on the left represents, maybe it's a light bulb, maybe it's something else that is using that electricity. So over time, we ask them to start to circulate and take some water out of the bucket as they go. And you can see that the bucket in the back, as they're marching around, the bucket gets more full and full. It's transforming some of the energy from electrical energy, or the chemical potential energy that was stored in the battery, to electrical energy, to whatever it is changing as a form of. So we use this analogy, and we have some notes in the packet to go along with it, like, how would this change if we repeat it with a 9-volt battery rather than a 1.5 volt? Well, what does that do? That means that their buckets, or their individual cups, can hold more voltage, hold more energy, which allows more energy transfer. And this is all kind of pointing towards power. Power is voltage times current. We could run the students through faster, or each student could have more energy per charge, as seen with a bigger cup. And in both cases, we can generate more power or more electricity. It can get transferred. So this analogy is one that is great that students interact with, and also that we have some kind of guided notes along that are printed in the packet 6P that go along with that, doing some definition of voltage, current, power, all in terms of the analogy and energy transfer. Bradford, do you have anything else with our analogy?
Yeah, other than to say it introduces the power posters. So power is power pattern. So power is current times voltage. They get it out of here. So there's a lot of good physics, but this is not that big. So really meant to be like a kind of half-hour, 45-minute activity in total. And that builds up some of that important background, electricity, magnetism. And then we move into students, again, coming off of Unit 5 with sound and waves. They make speakers, from scratch, a cup, a wire, and a magnet. I'm not sure I did the share screen right to share my audio. It's pretty quiet. So Okay,
here we have a speaker, which is really an electric motor. We're using electricity coming out of our player, going through a wire, and I have a permanent magnet for it to push off of. A speaker is a motor. So if we run this backwards.
Okay, so that's that first part, that students make a motor. They're turning electricity into motion. And, that's a fun type of motion to make a speaker. And importantly, so I want to kind of go and show in the packet, what are they doing here? So, a key piece of the physics called for in the performance expectation is that students understand how electric motors work. And so students will annotate a picture and show that, and this is actually like an hour or 2 hours, and that students go through this. There's a couple demonstrations that show that a current makes an electromagnet. So in any case, we're looking at that answer key for the packet. So this is already has the answers filled in. And so students realize that, oh, when you put a current, which again is here, graph literacy, we have a current down here, which may be from a music file, or in this case, maybe a tone generator. In any case, they have that electromagnet, and importantly, the North Pole is on the left side. So it's going to repel off of that permanent magnet that they're holding in their hand. So there's going to be a force on the speaker. It's going to thrust it forward. Then as the current goes to zero, that electromagnet turns off. It does actually have some momentum, velocity. But then as the current reverses, it creates an electromagnet with the South Pole now on the left. And that, of course, now is attracted to the permanent magnet, pulling that speaker back. And then, of course, depending on what kind of signal you send into the speaker, it will change how the speaker vibrates and creates the sound wave. But just as you've seen throughout the course, but definitely higher level, right? Here they have an annotated picture. They're using a graph to help them draw the picture, and then using the big ideas of science to explain phenomena. And so, nothing too long. And then also, energy is that cross-cutting concept. And here, just like we had before, but building on it, we have energy bar charts. So they're tracking the energy flow through a speaker. And then there's just even a couple extensions. But again, it's just so often we just know there's so much in the year. This is, of course, a linear motor, meaning that the motion is forward backwards. But of course, a lot of electric motors, think of an electric car, you want circular, you want it to turn a wheel. So there is an extension to build a circular motor, and that can be short and sweet. That could also be for students that finish early. That's a fun extension. It is there, but there's so much good stuff in this unit. You just got to be careful, eyes on the prize. We always said that we want time for electric guitars. And then at the end of this unit is where everything comes together on climate change. So again, also save time. Now we're just a day away from electric guitars. Also be thinking, have enough time for the climate change culmination aspect of the unit. All right, with that, I'll just quick preview it here, but I'm going to turn it over to Matt to talk about flipping this and talking about how electric generators work. You're muted. Yeah.
Yeah. Let me just say one thing about speakers. Speakers are, when students make these speakers, it's like magic. If you can't do anything else, they are just blown away. All it takes is a neodymium magnet, really strong magnet, coil of wires that's taped to a cup, and you can hook this up to a headphone jack, and it is. Students are blown away. And so this idea of changing electricity into motion is a big one for them, and super fun day, or a couple days you can go even dive deeper into it. So if we think a motor is taking electricity into motion, a generator is the flip of that. A generator takes motion and generates electricity. And so we introduced this in a couple of ways. You can think about it as a speaker produces motion, a microphone takes that in. We also have a FET that goes along with this. So Bedford, if you could click on the next tab over. So there's this Faraday's law simulation, where if you have they just got done with looking at and building coil wires and sending electricity through. Well, if we take this magnet and move it through the coil of wires, of course, we can make electricity. The big idea for them is that we can flip this both ways and change this electricity or this motion and make electricity. And we focus on this so much is because almost every energy source that we use besides solar uses this basic concept, taking motion and generating electricity. We have a quiz that goes along with this on the next tab, Bradford. Oh yeah, go ahead.
Do we want to jump? I'll quick show those two videos. So to just say what I'm saying about the
yeah.
speaker, and I'll try to play it right from the beginning.
Okay, here we have a speaker, which is really an electric motor. We're using electricity coming out of our player, going through a wire. And I have a permanent magnet for it to push off of. A speaker is a motor. So if we run this backwards, this is electricity into motion. We run this backwards, we should get motion into electricity. And then of course, we'll do electricity back to motion with this speaker. But let's check and see if I can make a microphone, which is a generator taking motion into electricity. 1, 2, 3, 4, 5, 6, 7.
So we have that one, which, you know, every student right after they make that speaker has that capability. And of course, that's a nice, it's really helpful to have a nice big amp. And if you can talk to your band teacher, a lot of band classes have very powerful amps in the school. And the bigger the amp, you know, just the easier it is to make it work and make it loud. And then the other piece that they do is, especially if you built those inexpensive guitars in Unit 5, we come back and they can just sort of rip apart that speaker that they made and electrify their guitars. So I'll show that quick.
Oh, yeah.
So here's acoustic.
Oh, yeah. It's supposed to be.
Okay, here is the magnet. We got our coil sandwiched underneath there. And just 2 wires going into our.
Okay, nice. So just assuming some familiarity there, but you know, a changing magnetic field creates an electric field. And if you have a wire there, that's going to create a current. And of course, how quickly that magnetic field changes depends on how much the guitar is vibrating. So it's a nice one-to-one system there, and really engaging with students. All right, with that, I'll turn it back over to Matt to just talk about the quiz. Oh, sorry. Yep.
Yep. So we then have a quiz there focusing on, you know, what are the basic physics of motors and generators. And we want to kind of come back to this big idea of science of using models and systems, and in this case, energy bar charts, come back again and help us with an explanation. And so you can see that we use energy bar charts here where we're talking about like chemical energy from an arm or something that is getting transformed into transferred and transformed into kinetic energy, and then that energy gets transformed in or transferred into the light and electrical energy that is in the coil and the light there. So we're able to think about tracking our energy through time in different energy bar charts that allows us to look at what's the big idea behind motors and generators. If you scroll up, Bradford, you can see there's similar ideas, thinking about force and the electromagnet that gets created by the coil of wires. And that allows students to kind of get back to that idea of north-south pushing and pulling, and connect those two things, the speaker, which is a motor, and a generator, which is creating electricity. And of course, we want students using, you know, diagrams, charts, graphs to be able to explain the big ideas of science.
All right, so now we are going to change gears a little bit. So we took that deep dive into the physics, and I kind of want to show the image. So I think that's on this one. No, sorry that I jumped around. Oh, now I'm regretting it. right here. Okay, so again, Voices of the World, we took that deep dive into all the physics standards that we had, although we actually still take a little bit of the physics standards into the wind turbine, but also this is our culminating engineering project. So the wind turbine, and it's a good one. But before we actually start the wind turbine proper, there is that idea of that discussion I hinted at of scaling up, right? Like we're not going to power the world with electric guitars, so we got to scale up. And there's just a lot of neat resources out there. Lots of times we lose, which is a good problem to have. You know, everyone starts clicking around. There's some real dynamic, some websites that, you know, this is from the state of Oregon. In any case, you can just see how, I don't know if maybe I will just pull it in. You can see it. So in any case, you can just see the energy mix of Oregon and how it's changed over time. And again, by 2040, we're already off coal by coal power plants within Oregon, but there is coal by wire. So Eastern Oregon has some power plants that feed it in Idaho and Wyoming that are coal generated. And any case, there's this one and there's a few more sites, but we were just going to not get pulled into it. So I'm going to just show that. There's a couple other interactive maps that show the entire Western United States. And it's just great. Students are just asking questions and they're really curious. So that's a great crossover before we start in on the, I'm not sure why I have this tab right here, but I guess it is. It's this one that, you know, so students do bridge how, you know, where there's that question, and I'm sorry that I should have showed that. There's another map here that I didn't show. There's another, I was talking about it, but I didn't show it and I don't have it already open. So there's a map that shows where all of the power production, and especially in Oregon, a lot of the power is hydro, and those power production plants are very far from where people live. So that's a great introduction with the storyline of talking about moving power or electricity around. So, you know, it's developed in one spot and then has to make it to the end users in a very different spot. So high voltage power, why do we have them? Again, that's pretty short. So we wanted to keep it really short in the webinar. Okay, so that crosses over. I just wanted to not hop from electric guitars to wind turbines and not show how we do keep the storyline going and keep it it has a great flow. So in any case, we do arrive at the engineering a wind turbine. And so often, again, we just want that critical reading. So they got the request for a proposal. There's some critical things they got to read closely. There is a typical wind speed and there's a max wind speed. And of course, those are both key numbers. The typical wind speed will help you figure out about how much energy or power you'll get out of the wind turbine. But in terms of engineering, you got to make sure this wind turbine doesn't blow over. So both of those numbers, they got to read, and you know, someone that just looks for wind speed and puts it in is not going to be as successful. So again, it's only one page, but each paragraph has some real things that students have to get out of it. And the slides support you in, you know, helping students critically read that. And then, you know, again, we got that wild guess, and I'm catching myself because I was about to just show every aspect, but this should feel very familiar, right? That there's the initial data collection, and I actually want to hop to it. So we jigsaw it like we've done with so many labs and even some of the engineering projects. One group will look at how power versus angle. Another group will look at power output versus number of blades. Another group will look at power versus shape. And these are the four, and power versus total area. So these are the four that come up again and again. And we suggest having these things pre-made. And that way your data collection can be done very quickly. And as we really want, this allows for students to look at 4 graphs, and now they get some money and they get the chance to be creative. We really want them to realize engineering is creative, but we also want them to realize it's data informed. So here's a nice mix of it. If these blades are pre-made, even if things are flowing well, you could start to collect data on day 1. Sometimes it spills out into day 2. But then day 2, they finish the data collection and they're talking science. Right now, they're talking science. How does the angle affect the power output? That is a science question. But then in light of trade-offs with cost, on the next day, when they get to build the blades however they want, including ways we've never looked at in these 4, like students like to twist the blades, students like to change there's a sweet spot coming out of those fans. Where you put the same size blade will have a very different efficiency depending on how close you put it to the axis of rotation. And those are all these little things that students figure out and builds their engineering identity, that they figure that out and make ones that outpower any of the ones that we tested on that first day. But then let me just wrap up by saying they talked science here. But then in light of the trade-offs, yes, more blades is good, bigger blades is good. However, you don't have money to do both. So they have to do a trade-off. And that's where we say they're talking engineering. How do you get your biggest bang for your buck? Before we wrap up there, I'll just throw it over to Matt to let him add.
Yeah, so just a few kind of teacher notes for this, that don't be surprised if your class's data looks different than this data here. So different classes, depending on the size of your fans or things like that, you might get that power versus shape graph looks different. The big key is that we want students to be using the data to think and analyze and make their decisions. So even in our classes, that happens at times. The other thing to note is if you look in Bradford won't find it right now, but in the slides there are like pre-made like some suggested pre-made cutouts for these. Having pre-made blades, I know you mentioned it earlier, takes this from a 5-day activity to a 2 or 3-day activity. So if you are having students cut out the blades and glue them on and things like that, that just takes longer and longer, and we're spending more and more time looking at that. If you want to be able to do that a little bit quicker, having those, a power versus angle completely set up, that's very helpful. One last kind of teacher tip that we do at our school: we don't have enough blades or enough setups for every classroom, and so during this time, which will happen for us in a couple weeks here, we set it all up in one classroom and just switch classrooms. If that's that kind of makes the setup and tear down a little bit more manageable for our classes. So those are just little things that we have seen that help being able to make this a little bit more manageable for us as teachers there. And with Bradford, do you want to do solar next? Talk about solar. Yeah, and actually, let me say one last thing. And again, we chose wind turbines because wind turbines are one of the fastest growing sources of power, especially in Oregon. And we wanted to use that straight off of motors and generators. How do you generate electricity? Well, you have to have some sort of energy in, you have to make motion and get electricity out. We're also going to focus on solar power because essentially all of the other power production works like a wind power besides putting something different else in. Solar power works quite differently, and which is why we want to do a little slice of engineering on it. So I'll hand that off to Bradford here.
Great. And always it's a fun one to start with. And again, we weren't in present mode there, but there you go. Just the phenomenon. Why the difference in mounting of solar cells? So we got the Galapagos down here. We got Oregon. This is at the I-5-205 intersection. Some students have seen that if they live locally or in the Portland metro area. And then up in Alaska, that's quite different. And the great thing is students have ideas. And we are about to introduce a mathematical function that lots of times when teachers hear it, they're like, whoa, 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 you're going to do this with freshmen. And I just want to say, like, it turns out not to remember that students are used to just playing in Desmos. So they don't think of the function the way a math teacher does, or even a physics teacher. It's just sort of play in Desmos to find it. So, and this is neat. And so in any case, so they go and try to optimize the angle. So this phenomena is a great discussion. And then I was going to jump to them. They go and take data themselves and changing the angle of the blade, and they get a bunch of data points, and it's actually kind of fun. And a lot of them, in Desmos, we now have 3 sliders. So lots of times we had just 1 or 2 sliders, depending on the actual lab. And now there's just a lot that they can do. And again, I've seen a lot of teacher concern about it, but most of the concern with students are coming from when they, like, the ones that really want to make it fit every single center green dot. But almost everyone just takes it as a challenge to figure that out. So in any case, I'm not even trying to do it too well, but okay. So in any case, we just see that, and I kind of knew what I was doing, I guess, but students might, yeah, I don't know. But you can just imagine they get in there, they kind of see that they got to do it, and oh, okay, that's going to here. And the neat thing is, we know this is a mathematical model. So A means something in the real world, and B means something in the real world. And they already know from that phenomena question, B kind of shows you at what angle do you get the most power out. And it's really obvious when you point it at the sun. So like, no one's intimidated by that. Even students that don't like math, they get, yeah, B, oh yeah, it's 32. And my angle was 32 when it was the most power coming out. And they're like, that's when I was pointing right at the sun. Like, it's not intimidating from the student side too much. A and C, it's a little bit hard to tell the difference, but there is some key questions that lead students. And I'll just sort of quickly say it, that A depends, is really says how much power are you going to get out with your solar panel, right? I mean, if you have a solar panel that doesn't work as well, A is going to be a little bit more flat. And if you have a really good solar panel, or if you go somewhere with a lot of sunlight, that just totally makes sense. So technically we call it like the amount of energy that you can harvest directly from the sun. And then students do even notice this, and especially in Alaska, this is really true. You can sometimes get, you can not point it at the sun and still get energy out. So C is the scattered light. So especially in Alaska with all that snow, you can point it away from the sun and still get some solar power from that. So in any case, just culminating data discussion for the physics year, and it does introduce that new pattern. But again, I'll just say, going back to the Galapagos, Oregon, and Alaska, walk students through, and of course they might need some teacher guidance too. So they've gotten a lot of the ideas around how to do a data discussion, so you can be more a guide on the side and stop by the groups that might need it. And then this 4th box right here, just for clarity, is the data that they take that day. So this data was taken on the equinox, which is important because then we know that the solar power is the same for those 3 locations, but it may not be the same on the particular day you do your lab. All right, so just want to zoom back. I keep missing it. I want to zoom back out to the big level and say, this is a chance to do a new one. And sinusoidal, right? Like, students have a sense of accomplishment that they make sense of sinusoidal. And usually by the end of the data discussion, almost everyone does, just in the way that I said. B is when you point it at the sun, and that's going to depend where on Earth you are and what time of year it is. And it totally makes sense that you should have a bigger wave if you have more more harvestable energy. Okay, so again,
Let
that's,
me-
oh yeah, I'll hand it off to you.
Yeah, just a few again tips when you're thinking about doing this. We have the Vernier solar cells. We connect them to the energy sensors that we use, also that we used for the wind turbines, so they're familiar with the technology. And you really do need to worry about or think about light that is scattered off of different things. It doesn't necessarily have to be a bright sunny day. Of course, that is oftentimes best. But do think about where you, if you do this, I would suggest like going and testing it somewhere in wherever you're at. So for example, we have a courtyard area, but our courtyard has kind of really bright concrete around, and some of that reflected light off of the concrete comes up and hits our solar panels and and throws off the data a little bit. So last year we went out to the track or the football field. That just kind of allowed a little bit better data, though it does work if you are closer to a building. You just got to think about reflected light that might be happening. So getting out in a more open space is a little bit gives you a little bit cleaner data as you go out. And I do like students to get that solid like sinusoidal idea when they go out. I like having them point it straight up at the sun and see that if they're equal amounts on either side of that peak, that they're getting equal amount of power output. So those are just a few things that happen when you are doing that. The last thing is you want to hook it up to a load, maybe like a resistor or a light bulb. In the zero supply list, there are something called variable loads. You need to hook those up so that it has something to send the light through or send the electricity through.
And depending on what the new Vernier sensors have that built in to the
right.
actual, but if you bought them a few years ago, you need a separate resistor load.
Yeah, good.
Nice. Excellent.
You
So
want to peek back? Yeah.
Yeah.
Go ahead.
Yep.
I was just saying,
This is the
look at
one.
the agenda.
Yeah, should we? Okay. Going back to the agenda, because there is so much in this one. So two things to note, not even going to show it because it's basically everyone needs, or almost no one has time for this one. And it's difficult. Wave particle duality, that is in the performance expectations, but we're always asked, what do you recommend if you don't have enough time? And this is unfortunately probably the first one, that wave particle duality. Whoa, that is just one performance expectation, but that has weeks and weeks. If we were really going to explore that at the depth we were hoping for with all these other performance expectations. But if you do, we have really done this, and it's a 1 day or 2 day, depending on if you show demos and some other things. There is an extension for wave particle duality. It's there, but just most people don't have time. And it's nice that it does really fit with a solar panel. So that's a good reason to put it here. It's standalone enough that if you just had 1 day, you could use that as a, I was going to say, I don't know if a sub would, depending on your sub, if they would feel comfortable with it. But there is that there for you. All right. But in terms of the storyline, as we said, diving into climate science, and there's a lot of earth science targets in this unit. So wanted to slow down here for a second and just show you that in the slide deck, and I have too many tabs open, there is a teacher note that has links to the K-12 science education, which is what the NGSS was based on, the framework for K-12 science education. So there, it's only 5 pages here and 5 pages there, and that's really good. So it just really more explicitly talks about what the standards are for students to learn around weather and climate and global climate change. So those are definitely worth reading. We want to just call that out because there's a there's a lot of new information or I just saying in the past we've had teachers that have said they were physics majors and never had anything on the weather and climate. So that's just a resource there for you. Okay. And then again, just that picture of the storyline. So we're here. We've looked at the two major wind and solar, as Matt already mentioned. And so now we're scaling up back. We're still that 50-year energy plan's really alive. We've touched on it many times, not in the webinar, but in the day-to-day of the story of the unit. And here we are looking at, okay, so we need to understand the climate impact of different power production means. But to do that, we really need to understand a little bit about how the climate works. So that launches us into building a strong foundation of earth science. And just want to call out a couple things in particular, the timescales of climate versus weather. And the NGSS calls out for not only like day-to-day versus year-to-year, but even decades. And there's even a couple of references to, you know, cycles that happen on the hundreds of thousands to millions of years. There was a lot here. So the one other piece I was going to discuss, and then I'm going to throw it over to Matt to finish off these details, is just to show the three big ones. And this was supposed to be in present mode. All right, so we can get surprisingly far with just three factors affecting atmospheric circulation. So one of the major ones is the different intensity of sunlight over the earth. And again, you know, just to see how interlinked all of this is, right? Go back to Galapagos, Oregon, and Alaska. So again, just want to show you that students have are already thinking this. So anyways, that terminology is, I don't know, a little bit unavoidable. We really do want them to realize it's the different intensity of sunlight over the earth. The equator really is going to heat up more because it has more intense sunlight. And so no surprise, the equator is warmer. The other one, again, students come up with all these, but I'm just kind of showing the slides. The Earth's surface varies, you know, oceans versus land versus mountains. And then the fact that the Earth is really, really big and spinning. And this, the simplest one, just to show you that these resources are here, is that the equator, the air is warm and warm air rises, we know. So, and cold air sinks. So it's no surprise that the biggest wind on Earth, we're always thinking east-west, which is of course very important, but the biggest wind, really the largest airflow, is from the poles to the equator. That cold air comes and displaces the warm air up, and that warm air then starts to fall back down towards the poles. And just a neat fact, I thought this was, I learned this, I didn't realize this myself, was that's why it's hard to cross the equator. There is tons of wind on the equator back when you had sailboats. It's just all the wind is vertical. So you have the doldrums, not because there's no wind, but because all of the wind is going up. In any case, just the last piece of the puzzle is the world is really big. So it's not as simple as that first model, and the air doesn't make it all the way to, you know, the warm air rising. And of course it rains a lot. When warm air rises up, cools off, it rains. And then it starts to flow towards the North Pole, but it cools off and settles before it makes it all the way to the pole. And the last thing, just because I think this is fascinating, where are all of the deserts, minus rain shadow deserts from mountains? They are right there at where that Hadley cell, where that cold, dry air, it's already rained out. So when it's coming back down, there's almost always dry air. So if you look worldwide, all of the deserts line up on these so-called Hadley cells. And then of course you have another rain area, and then you got the boreal forest there. All right, so lots of neat stuff in that. Just want to say, we wanted to show a little bit more of the resources with this one. And I know I missed this couple things, so I'll throw it over to Matt just to fill in some of those gaps and get his perspective.
Yeah, so we're looking at getting our background and these ideas of of climate science, looking at the different various factors that affect those, and then we also are going to be looking at dialing in at climate models and really kind of building and using a simple model that explains a lot of different factors. So the NGSS specifically calls out 10 different factors that affect both warming and cooling climates. And we'll use those models and look at those to get that. The other piece that I wanted to say before going on is students do have a little bit of background on this from the climate impact criteria that we mentioned at the beginning. And they were looking at how do greenhouse gases affect the climate from different energy sources such as coal, natural gas, hydroelectric, things like that. And so this is an opportunity to get that was a kind of an initial understanding. This is an opportunity to get a deep dive in what is truly affecting the heat that is both entering and leaving the environment. If Bradford, if you don't mind going to the next tab there, there's two different ways that we have this. Some of this is in the slides. And this is a Desmos activity that kind of was born out of the pandemic. And this is one that not everything is, in my mind, needs to be on Desmos. We do have this on paper version, but this is just a really good one that they can kind of interact with within the Desmos. So we want to bring it back to this idea of energy flow. What creates a warming and cooling climate? And this is a very simple model, and different aspects of this are very important. So on that last slide, Bradford was showing that, yeah, if you don't mind going back, just like light energy comes in from the sun, some of that gets transferred to the ground, but some of it is reflected off to space. And then on the right side, we start to look at heat, that like thermal energy is also being emitted by the Earth's surface, and some of it is getting absorbed and re-emitted back down to Earth, and some of it escapes off to space. So in this simple Sankey diagram, we can allow them lots of iterations at playing with the model and looking at the model in different ways and seeing what affects a warming climate, what affects a cooling climate, and thinking about very specific effects like greenhouse gases being released into the atmosphere and how they might affect the climate. So Bradford was showing on this next slide, like he was playing with some of those draggable arrows, and you can see students can start to generalize and notice what causes a warming climate, what causes a cooling climate. They can start to look at that energy flow into and out of the Earth system to kind of get that idea of cooling and warming climates. From there, students are left to do a couple things. Let me think, Bradford. Yeah, they summarize, we talk about energy in versus energy out. And using this model, they quickly can start to look at different effects. So for in this case, the one that we want students to drill in first, the first and maybe most important for just think about is what do we have to change to represent an increased CO2 in the atmosphere. And so this allows kind of easy manipulation of the model, and they could take that red arrow that's going out into space. More of the CO2 in the atmosphere is absorbing and re-emitting the infrared heat back down to Earth, thus capturing it. And this might represent that increase in thermal energy. And then when they go to the next slide, if you leave it like that, Bradford, it copies what they did on the last slide. So those are the changes Bradford made. And then it allows them to say, you know, what does this do? Does this show a warming or a cooling climate, and why? And lets them explain their thinking. So they can get kind of quick iterative feedback on warming and cooling climate models based off of what they did, and get feedback from each other. Also getting feedback from us. How does that model explain what is actually happening in the Earth system? Of course, there's several other ones I don't think they're maybe worth showing here, but you know, volcano eruptions, things like this. These are all chosen specifically because they were called out in the NGSS as the factors that that were important for NGSS in the to focus on and hit on. So looking at that warming and cooling system. Bradford, do you have what else do you want to add?
Yeah, good. I just did a time check, which we really wanted to make sure we gave time to play with the 50-year energy plan, because we just had gotten the feedback that if people didn't try it, it just was daunting with the resources that were there. And we have. In fact, I almost think we kind of rushed. So there's a lot of little things that we could sprinkle in, but I think you got this one. So that was, I think, good. So with that, I'll go to this next piece and then get us started on trying that 50-year energy plan. Do want to just point out again that there is a lot of resources here to go and explore climate change. And so, you know, data from NOAA and NASA. This one, I guess, is just the graph, but a couple good videos too. And I want to just make that plug again. If you know of really good videos, always, it would be great to share those if you're willing. So you just want to, there's a lot more. One of the projects that we had on the one, I was tempted not to say this, but the negative critical feedback. Whoops, what happened? Oh, okay. The critical feedback on this is sometimes there's one, you know, how do students can figure this out, do a little bit of research, but it would be better if we turn this into a stations. And we have lightly done that already, but it needs some better videos. So if you do have good videos on those 10 factors, that would allow us to transform this to a more of a station activity or a jigsaw. So again, if you have those videos and you're willing to share them, the easiest place right now is the idea capture tool. But then also there's just we do think these videos are good already, but you could easily add more. But this video we wanted to just show, you know, it's a common one that a lot of people have already seen, you know, the atmospheric pump. But I really just wanted to get to, because it's so called out in the performance expectations, you know, talking about some of the longer trends since, and that's about the detail that we go in what's covered in this video. So I just wanted to call that out. With that, I want to zoom back out and that, you know, depending on how much time you have, there's a lot more you could say here. But when you do wrap that up and transition, we have that the revised, both because of especially in Oregon, if you're in Oregon, that the laws have changed. And there's been some iterations that have really helped. So I wanted to slow down here because I was going to jump to the changes. But if you are totally new to the 50-year energy plan, that's that culminating part of that engineering project. There's some writing that we're going to not fully dive into the 50-year energy plan and show how we leverage this to get students to write and use the big ideas of science to explain things. But in any case, here it is. So here's hydro. So you can tell I'm a kid I'm a father that has kids, because I think of it as like the Pokemon stats. Pokemon stats. So hydro has a land use impact of 4, and this is on a scale of 1 to 5. We have a file of where these numbers came from. The climate impact is 2. There is some greenhouse emissions from hydro, and then a lifetime cost. There's a reliability, and this is a nice touch. If they go too quick to solar or don't co-invest, solar is in one sense on a 24-hour scale unreliable, right? Solar doesn't produce during the evenings. So they need to co-invest in smart grid technology and energy storage. And so you can see solar reliability, because if the reliability dips too much, that's one of the constraints. One of the constraints we came up with on day 1 of this project is supply enough energy for Oregon's needs. So if the reliability dips too much, they will get a thumbs down. Now, so in any case, if they don't invest in energy storage and smart grid, that will happen. All right, so in any case, each of the power mixes as they are have stats, and those feed into making sure they have enough energy, enough usable energy needs check, that essentially the way we handle the economy can't handle too much change. So that's the percentage change check. So in the 2010s, it changed by about 15%. And then in the coming years, in the coming decades, we need a lot of change. If we are going to get completely off of fossil fuels, you have to embrace that there's going to be a major change in the energy structure. So it goes up and then it backs off again. And then I already mentioned the reliability. So those they need to make the energy mix, and that's in those green. They would change it. I'll show that. So actually, I'll show 2 things. Coal, we're at 32 and we got to get down. So I'm going to put it in negative. It's the only one that needs to be negative. But I'll say I'll say negative 16 to start. I'm not sure that's the best move, but okay, negative 16. So I've even lost energy and now I got to grow it. And I know I want to grow wind. And let's just say I put in 16. Oh, I get the red bar. Why? Let me go look. Oh, my max change. We can't build that much wind turbines in that decade. So I actually see that my max change is 12. So I'm going to go to 12. And then I might even add some geothermal. I'll just put 8. Okay. So as we change those numbers, they get immediate feedback. They got 101 energy units, but they need to get up to 110. So they're going to have to they got to grow. Oh, with that geothermal, it just went up 8 to 109. Okay. And then down here are the criteria, and you can think of those as, the sliding scale of how good they're doing. How good are we doing on land use and the environment, the climate impact and air quality and lifetime cost. And one thing I'll say is some students want this to be happy in the 2020s, but there's no way to not get happy in the 2020s, because it is going to take more than the 2020s to reduce the climate impact of our power production. So just, be ready for that. But in any case, I want to finish up the overview, and then I'll hand it over to Matt to catch what I skipped over. Is they'll do this for each decade. And the new thing, so people that are new to this, something that is sometimes if students just looked at the smiley faces, they kind of stopped. Once they got a smiley face, they stopped. And, that's not horrible. That's a good thing. A lot of good things already happen when they try to get to smiley faces, but we didn't want them to stop. And we wanted to let them, if they wanted to push forward, we added the total score and a happy face. So like, if someone prioritized climate change, which is what a lot of students do, we don't want to, all 3 of these are important: land use, environment, climate, and lifetime cost. So sometimes a student might get a super happy face in climate, but an unhappy face in the environment. And that is not no one in Oregon wants that. So that doesn't represent that project very well. So in any case, they get a individual score and then they get a culmination score. So that was what was updated, and that we did release last year and just got a lot of positive feedback. The one other new one, and I guess I should go to the key. I don't know that we have that open. Okay, well, I'm going to throw it over to Matt and I will open the key and just show you that now students, after they make their energy mix, they create that Sankey diagram, that same one that we were showing in the wind turbine. Again, I'm assuming if you're familiar with that, so sorry if you're not. Do we have an example one? I think we do. They now make Sankey diagrams in Google Sheets to show their 50-year energy plan. And that works a lot better than copying and pasting the spreadsheet numbers, which no one could read. So just another change that everyone likes, and it just really gets students talking, because they'll look at this graph and go, oh, I never thought. Here's one tip and trick. Yeah, actually, I know I'm going too deep. So I'm going to step back, and Matt, do you want to jump in and share your thoughts?
Yeah, just a few things. As students are initially looking at the 50-year plan, some of them jump right in and understand, what the game is, trying to get all thumbs up, trying to get smiley faces as happy as possible. That doesn't always happen for everyone as we first start. And so there is some prodding of some questioning that we kind of like to go through. So thinking about, we didn't mention this earlier, but students have already written about what their number one priority was. Was it, climate, land use, or lifetime cost? And so we want students to think about the things that meet their priorities. So if you were going for climate, wind would be a great area for you to invest in. So because the climate score is so small. So having those conversations about what I'm doing, why am I doing it, are very helpful. The other thing that I wanted to mention is that students don't know how much to add each time, and we really want to harness this idea. This is computational thinking. This is using a computer to do some of the problem solving and thinking for us. This is set up so that it will give you some feedback, and we want students to, maybe they go too hard on something. We want them to iterate their plan and realize that this does take time to plan out. We do want to think about this over the course of time. We can't just, do what we're doing without making a plan for that. So those are things that come up for students that, maybe it's okay to encourage to mess up and try different things, because no plan is going to be perfect on the first time. You definitely have students who are trying to min-max everything, get everything absolutely perfect. But those aren't the students that we're worried about engaging at the very beginning. It's students who are reluctant to try it. And I would just want to encourage that, talking about what their priorities are, things that they want to do to start that. And oftentimes it's helpful to do a decade or two with them so that they can start to get that idea of there. Ultimately, in terms of the project, I think we do want to give you some time to work on this, but maybe let's talk about the end 5-paragraph essay and then come back. That they're not graded on how good their plan is. They're graded on evaluating, and these again all came out of the evidence statements from the NGSS. They're graded on how they can communicate their plan, a competitor's plan, and reasoning about the best design and thinking about limitations of their plan. So there's 4 sections here, 5 paragraphs, because section 2 requires 2 different things. In the first paragraph, they are that's kind of almost done on day 3 of class. They are looking at the engineering challenge, describing what they're trying to do, what criteria and constraints there are, and what might happen if the plan's not implemented. Coming back towards the end of the unit, they're looking at their evidence. So their evidence of two different competing plans. There's their plan, screenshot of it, and the mix of how their energy changed over time in a competitor's plan. And they're just describing the strengths and weaknesses of those two plans. That's in that section 2 there that you can see on the screen. In section 3, they are reasoning about the best design. They're saying which of the two plans fulfilled their priority the most. And I always tell them it's okay to choose your competitor's plan. We want to describe the differences in them and conclude which plan you find better. And then finally, limitations of the plan are often some of the most challenging. Of like, what challenges do you envision implementing the plan? How does it actually match reality, and how does it not maybe match reality? What might happen if any tech breakthroughs happen with their plan design? We do have lots of supports that go with this. And Bradford, if you click on the next tab over.
And I might even, let me jump in and say this one comment, that if we were started, especially with the vertical progression of the pattern science sequence, of having students write a 5-paragraph essay. And if that's not the right fit for your classroom for just a variety of reasons, each one of these statements is right from the evidence statements. It is really the thinking we want students to do. But if that's going to require more time than you have, not to lose, not to throw out the baby with the bathwater. I just want to open it up that many teachers do actually just use the graphic organizer that Matt's about to explain as in place of the 5-paragraph essay. Of course, there is a good skill of taking that graphic organizer to the 5-paragraph essay, but your classroom and you got time constraints and a lot of other things to manage. So just want to throw it out there that if you saw the 5-paragraph essay and are like, that's not the right fit, still take a look here at the graphic organizer, and I'll throw it back to Matt.
Yeah. And I'll just say, like, the other kind of issue, of course, with time and time as teachers, I have 135 ninth graders this year, grading those. And I like to have them turn it in over time by section and then grade each section. I don't grade the whole thing at once. That is just a helpful breaking in the assignment up into 4 chunks rather than having one big one. That's been really helpful for me in the past. And trying to grade it and give feedback in class. And I think that's actually the best, most effective feedback is I've been having them, when I do this, come up front on my screen. I'll have the rubric and grade it right in front, give them some feedback straight from the rubric. And if they want, depending on your policy for redoing or retaking, give them opportunities to do that. The one tool that we are having them use, and it's nice because the graphic organizer is very kind of lays out the paragraph, and this is printed in the packets in 6P. The packets don't all have these possible sentence starters in them. This is 6P support, you can see. So yeah, Bradford's going to scroll down to 6P. This is just the graphic organizer. So I will print the support packets and either give that to everybody or give that to students who I know will need them. And it has, some example, some support sentences within there. So when they're talking about their plan or the competing plan, gives them some support in writing that and really thinking through how that goes. So students are really able to, with that organizer, again, we've even graded just these organizers before, or taking them and moved them over to give them a kind of a rough draft feel into a document, and using those to be able to support their writing, and also the rubrics that are attached to assignments so that we can give them that feedback. Really powerful tools to help students write better and really feel proud about the work that they did in this culminating project in their 9th grade year.
That's awesome. A couple notes just to say is this is a time where again you could invite in adults. You know, maybe it's another teacher, maybe it's an administrator, maybe it's, if you're able to. We did have this vision. We've even talked to Oregon State University and PGE around having graduate students that are studying this. They're looking for outreach efforts. So you could have students explain their energy plan. And just like in the Bungee Jump App Expo Day, running it something similar to that. We're trying to actually large scale make this so you could almost sign up. That hasn't happened yet, so I don't want to overpromise. But in case if you just have a local resource that you may be able to do, that's been so it's been a great experience, and it's a really nice end of the year. Students are really proud of themselves, and they really have like something to say. So it's really nice to have them audience that they appreciate having. Okay, so I pulled up the key, which is also valuable to check if we're about to release you, and we really wanted to make sure we gave you time to really play with it, not just 5 minutes. But I just wanted to show a couple things. The key is helpful, just again, so you have to, at the end of each decade, achieve all thumbs up. You have to meet the constraints. And of course, then on the criteria, the better you do, the better. So again, you have to keep meddling until you get all thumbs up. And you don't have to do it at the first shot, but I will just say by the end, you want to, and then I just wanted to show that example graph. So on that second slide, this auto copies their plan. This is their plan. They don't have to do anything. It's already set up to grab the numbers they have from the previous one, but they do have to do everything to make this Sankey diagram. And I'll just quick point out, this is an energy bar chart over time, right? If you just look at above 2010, that's the energy mix for 2010. And so you can just see it's a continuous bar chart. I just wanted to make that connection that, again, graph literacy, we're just showing students lots of ways in this class to visualize data, and different visualizations make different things pop out to your audience. Okay. With that, I think we are there. So if we go back to the agenda, there is this try it out. So if you want to click on that and make a copy.
I also just put it in the chat.
Yeah, that's better. We thought we would open up breakout rooms. If you want to, like, there's two things that we wanted to do with this last time, and we have 25 minutes, so that really is good. Now we want to save 5 of that for answering questions. We're gonna, while you're in working on this, we're gonna try to answer the questions in the idea capture tool. But we want 5 minutes of us all coming back together. But we knew there'd be kind of two things. We knew there'd be resources that you have. So if you are willing to put them in the idea capture tool, that is awesome and really helpful. And then we really wanted to give you a chance to play with it, because it takes, and I want to just say this with, you know, there's students that they start this and don't want to do, and they kind of shut down. But I just want to say that we don't have to always, and I don't mean it that way. You don't have to, sometimes if you don't do anything, some students will say, like, they'll start talking about it and students will see that it's doable and they'll on their own re-engage. Now it depends on the student. So I'll just say that some students are a little bit overwhelmed, but that's a little bit intentional. We want them to kind of look around and feel, you know, the least amount of help to be successful. And that might be just right from the get-go, help them with 2020. But at the same time, once you help them with 2020, there's some students that they can just run with that. And so it's just, I wanted to put out the warning, it can sometimes be too helpful if you do 2020 perfectly with them. That's all I wanted to say. So with that, if you have it open, we're about to open up some breakout rooms, and we're just going to make it optional. You can decide to join in. So if you're here with a colleague and you want to jump in a room together so you can talk, or you just want to get in a room and talk because there was a lot of material. We didn't have a breakout room session in the middle because we were worried that we would get here and not have enough time for you to actually try out the one, and I'm catching myself talking a lot, so I'm going to step back and get those breakout rooms open, and we'll give you some time to play with it.
I got him, Bradford. So I was going to make, let them choose. I think we'll spend maybe just like 10 minutes. Do you think? And if you want to, jump in with a colleague and work on one of those, just choose your room at random. Just made, 10 rooms for you to choose from. Oh, I have a countdown on them.
And we might have just over 10 minutes, but in about 3 minutes, we'll start in the main room and do 2020. But just to give you 3 minutes.
Good. So we hope that was at least some time to dive into that 50-year energy plan, especially with the new changes in mind there. Wanted to just give you some time to be able to do that and play around with it. And would be definitely willing, maybe after talking about the idea capture tool questions, to talk through any verbal questions that people have regarding that. There, did you have anything you wanted to talk about with that, Bradford?
Other than, I was going to say, we did respond to everything in the idea capture tool. And so while it was fresh, maybe see if there was a burning question about the 50-year plan, so as to not come back to it. Did in the chat or verbally, did anyone, was there any questions or comments on the 50-year energy plan? I pulled up the key here.
And of course, with the 50-year plan, there's lots of different possibilities. That's one possible solution.
Yeah, which is very intentional. And maybe one thing that addresses, while it's up here, I'll just say, there were some trade-offs in making this 50-year plan work in spreadsheets. So I was trying to, it was one of the later questions about the lifetime cost, which I haven't fully read and wrapped my head around. But I'll just quick to say a couple things here on yes. Well, a couple of the things that really that stood out and were very intentional was that reliability, but I think I already kind of talked about that. And it will take time to get people happy. There's a lot to say here, but I will point this out. So if you go to the teacher calendar and scroll down to obviously this area, I'll point this out. So here's the resource file for the power production values, and that gives some of the sources. And again, it's not even that simple. We really did have to talk to Bonneville Environmental Foundation people, Oregon, because those are oftentimes national or worldwide numbers. And like biomass, Oregon gets a lot of its biomass by after they pull corn kernels and can it, they have the corn cob and burn it. Some other places get biomass by wood or trash. And so it's really hard to get the exact numbers, but a lot of this, it's a 5-point scale, so it's not as sensitive. The real goal is getting students to wrestle with some of the system levels thinking around climate change. So there's a lot of personal decisions to be made, but then there's also things that we need to do as a society. So that a lot of those were informed from those discussions, and an educational tool to have those discussions. All right, with that, I know I'm catching myself probably starting to ramble. So I'll throw it back to Matt and say, maybe we want to just, if we do want to just go through the questions and add anything, or do we?
Yeah, we can do some of them kind of a little bit quicker. If you had to shorten their units, the whole storyline could live without the wind turbine and solar cells. While they're both super important and engaging, you could for simply get the problem, talk about, introduce the problem for a couple of days, dive into climate science, and then do the 50-year plan. I think there was just a little confusion on what we meant from 2022. The Oregon Department of Energy releases their energy reports quite late, and by this time last year we didn't have the 2022 report, but we do now, and so we will go through and make sure that those are all updated with the newest report.
And that's in the coming week. So if you've already started the unit, that might be an issue, but if you haven't started, you probably will have the updates.
Yeah, quizzes meant to be graded as formative or summative, really depends on your classroom and what we're doing. This year, I assume at our school, we likely will have them as summative and grade most of those. Do you want to take the next one?
I would just say that for us, a lot of times it is, I'm going to talk too long. So I'll just say, if it's at a spot where we are ready to summatively assess them, then there's closure, like that. The electric motors, we move on from electric motors in the rest of the unit. So it makes sense to have that quiz be the summative understanding, because there's nothing later in the unit that's going to enhance their understanding of electric motors. So there's that one, but there are pieces that might make sense to come back to, like energy, that might be a more formative assessment along their progress. Yeah, number 4, I do want to jump in because I don't know who wrote that, but I also feel the same way. And we originally did not have that in the energy portfolio. It was so, in a sense, heavy-handed. I mean, the criteria is right there, and then there's this little box that say the 4 criteria. There's 2 reasons for that, and you can have that discussion on the packet. I don't want to jump around too much. So here, this is what I was just talking about. Right? I mean, it's like just copy it over, no thinking. However, what they do before they get to here, oh my gosh, I have so many tabs. We wanted everything open, but that of course works against you sometimes. Okay, so they do this before they open up the portfolio. So you can have a very open-ended discussion on what are the criteria we want to evaluate. Now, I will say why did we then eventually go to that one? Because just as you saw now, the 50-year energy plan needs to be pre-coded. I guess you could maybe, if you really wanted to change it to the specific language, it just creates a lot of work. But in any case, that we eventually need these 3. But we have found just year after year, students come up with something very close to these, but we don't want to stifle that conversation. And I want to say that about this whole unit.
Yeah, and there is also resources idea or the question board, before showing them the criteria, they have thought about a lot of these things, and those can be found in the slides.
Yes, and so that is very rich, and it's not meant to be stifling, and the videos tend to go down those 3 as well. So really encourage that. And I wanted to say there's so many spots in this unit that you might add a whole extra day because there's something very organic that comes up in class. There's a lot of students that know a lot of things about this and have a lot of passions around this. So this is the core curriculum that we showed, but definitely want to encourage the there's a lot of student voice here. Okay, I gotta get back to here.
Yeah, typically we have students do it individually. There's most of the time they get through that. We have enough time to do that. If they did copy, it would be a hard time to have a hard time comparing and explaining it. The rubric, I linked one of them there, but they're all under 6 CER. So Bradford clicks there. Rubrics down there at the bottom.
Yeah, to show it. They're all in this one, but maybe it makes sense to have them in the key as well. But as soon as you click on a section, it'll be in the bottom of the section. So that's the right here, and then back to, sorry, I got so many tabs. Okay. So that's the for the answer.
Yeah, thoughts of essay writing in light, especially of AI writing. Definitely still thinking and reeling and trying to figure out how we're going to harness AI. I believe it's not going away. It's only going to get more. I'll say, like, this year we've already used AI image generation to draw shoes for us, which was awesome. So when they were designing their shoe, we had AI do the drawings for them.
And let me jump in with just that one question that we keep coming back to. And aside from cheating, which again, we have to figure that out as well. But one thing that hasn't changed, we didn't do writing because we needed 30 essays explaining to us how speakers work. We were doing writing because of the educational process that writing goes through. So, you know, that is what we're wrestling with. Just because AI can write it, and again, if they were doing it to cheat, then they're of course not going through the educational process. So that has that obvious problem. But yeah, but then there's also just the question in there too of like, sometimes it's fun to mix up the assessment, keep it, you know, stay with something long enough that you get good at it, but you got to mix it up enough to keep it fresh. So that is a perennial question. And I'll mention that the core curriculum really has that vertical articulation. So we do try to stay with things long enough, but there are times even in our own classrooms where the idea of writing another conclusion is, you know, falls flat with everyone, teacher and student. So you got to mix it up. Yeah. I'll cut myself off.
Good. Let's see.
Yeah. Ooh, yeah, number 8. Yes, I was imagining with the power supply that the teacher might have the hand on the knob on that one. But yeah, good comment. Fresh batteries are hard. And oh, we're at time. So there was 2 resources, and excellent. Thank you for sharing these. And if you come across some in the next weeks, please do share them. There are a lot of articles and stuff that are in the more nitty gritty that are optional, that are in there that are really good. And just some of those are in the last year, in the last couple months even, and they fit really well. We're at 6 o'clock, so we'll do our 3, 2, 1 countdown, which we really like. We'll stay on for a couple extra minutes. But if you are, I'll stop the share screen here. If you are willing to just unmute, and even if you're willing to video